In this video, I'm going to go over the trigonometry functions available in Affinity Photo's procedural texture filter. There are three main trigonometry functions: sine, cosine, and tangent. These originally are derived from the ratio between the sides of a right triangle. If you consider a right triangle, one of the sides will be the longest side. That's called the hypotenuse. The other two sides, you could consider an angle between the hypotenuse and one of the other sides. That side will be the adjacent side, and then the side opposite the angle is called the opposite side. So when looking at the trig functions, they're really taking a ratio of these different sides, the different lengths of the sides of the right triangle. So the sine is the opposite over the hypotenuse, the cosine is the adjacent over the hypotenuse, and then the tangent is the opposite side over the adjacent side. With the standard positioning of the right triangle, you would then have the adjacent side corresponds to the side that's aligned with the x-axis, and the opposite side is the side that's parallel to the y-axis. There are also inverses of each of these functions called either the arc function or the inverse function. The arc sine returns an angle for a given sine value. You could have the arc cosine, which returns an angle for a given cosine value, and then you could have the arc tangent, which gives you the angle for a given tangent value. The arc tangent has two different functions, atan and atan2. The only function that returns the full 360-degree range of angles is the atan2 function. In addition to the sine and cosine function, there's a system variable, pi, which returns the common value for the ratio between the circumference of a circle and the diameter of a circle, which is approximately 3.1415. And so that's given as a system variable that you can use either as an input or you can use it in your formulas. I'm going to start with a new document. I'll choose XGA, but then I'm going to make it 1024 by 1024 pixels, make sure it's in RGB8 mode, and create that. I'm going to choose black and fill it with black. I'll choose my move tool and add a live procedural texture filter, and I'll just move this over. I'm going to add a single equation, and I'm going to choose the sine of x. So I'm going to start with the sine function, and I'll just look at the sine of x. X is the position of the pixel, so that's sort of the pixel number starting on the edge at 0 and then increasing 1 until you get over to 1024 over here. So that looks like that. And in the scope, if I look at the RGB waveform, I can see a nice smooth transition. Starts at 0, goes up to 1, and then comes down to 0 again. And then there's a gap, and that's because the function actually goes negative during this portion of it. It goes down to -1, and then it goes back up to 0, all the way up to 1 again. So that's a full cycle, and this goes through a full cycle over a period of 360 degrees. So 360 degrees would be right here. So that's 360 pixels in this case. Okay, and then this would be 720 pixels, and then this would be 1024 pixels over here. Now, if I wanted to look at this negative area, I could do that, sort of trick it by making a copy of the sine, pasting it down here, and then just making this one negative. And I'm just going to turn on the blue so I get a cyan color for that. So the red is positive and then the cyan is negative. You can see the sine form sort of creating a series of lines across the screen here. Notice that it starts at 0, goes up to 1, and then decreases after that. I'm going to change this to the cosine. like that. Now this one is just a little bit different. It still has a series of stripes, but this one starts at 1 and then decreases down to -1. So the other one started at 0 and increases. This one is starting at 1 and decreasing down to -1, and then it goes back up to +1. So it's the same basic shape, but it's just shifted over a little bit. Now, also on here is something called the Radians, and if I click on that, I get just very fine lines. And if I zoom in on that, I can see that it's changing, going through a full cycle about every 6 pixels. And so that turns out to be, radians are based on the number of times the radius can wrap around a circle, and so it turns out that that is 2 pi times, and so a full cycle of radians is a little over 6 pixels. So you can use radians, then the cosine, sine, and tangent functions will treat the input as a radian value. This will also work with the inverse functions asin, acosine, and atan. All right, I'm going to stick with degrees. So the last one is the tangent function. So I type in tangent and tangent down here. Sorry, this one starts at 0 and then shoots all the way up to positive infinity, and then it starts at negative infinity over here. It comes back up to 0, forms sort of a lazy S shape if you were to look at the graph of this. So it's sort of hard to imagine that shape looking at this graph, but you can see that it's a little different than the sine and the cosine function. It's not just shifted. If you consider the ratio of y over x, then as x goes to 0, if y is positive, it'll shoot up to positive infinity, and then if y is negative, it'll approach negative infinity. Now the graphics processor just ignores that. Usually that would generate an error if you tried to divide by 0, but the graphics processor is set up to just ignore all those divide by 0 errors and still produce output on your screen. Another way to look at this is to look at the presets, and actually I've got a lot of presets, but if you go down to the basic shapes, there's a sine wave preset. If you look at the sine wave preset, if I look at the formula, it's using relative x and y coordinates, and it's dividing by the width of the document in pixels and multiplying by 360 degrees, and then by n, which is the number of waves. And then the height of it is controlled by this factor a, and that's the height of the document divided by 2. So if I set that all the way up, it'll take up the full height of the document. This is set up to show the shape of the sine wave. Now this one is set to 4. I'm going to change that to 2. And so 2, the middle of the screen is the 0 coordinate, 0, 0. And so this is increasing up towards 1 and then decreasing down to -1 as it goes across the screen. I can change that to cosine like that, and you can see the cosine starts at 1 and decreases down to -1 and goes back up to 1 again. So you can see how it changes. Now I'm going to change this to the tangent function to look at that one. So I want to look at the shape of the tangent function. So that one, as I said, has this sort of lazy S pattern. I'm going to decrease this a lot. And so this is shooting off to approach positive infinity over here, and then it abruptly changes and goes to approach negative infinity over on this side, and then has sort of an inflection point in the middle here. You can bring it down, see that sort of lazy S shape to it. Just going to start with a reset to an empty equation, and I'm going to add a single equation, and I'm going to look at the inverse functions now. The inverse functions, the sine and the cosine both divide by the hypotenuse. And so if I want to do that, right, I'm going to add a variable v equals the vec2, a two-element vector that's made up of rx and ry, so the relative x and y coordinates, divide by w. And I'm going to just look at that. So that's a basic coordinate system. Has the origin in the center. Now I'm going to add another variable, and I'm going to call this one hyp for hypotenuse. That's going to equal the length of v. So the hypotenuse in shader programming is just length of the origin vector. That's a good way to think about that. So now I can use the arc functions. So if I want to look at the sine, it's the opposite over the hypotenuse. The opposite is the y coordinate, so I'll use ry, or I can use v dot y. I could use either one, divided by the hypotenuse. And that's what that looks like. And I'll set this so it's only on the red channel. You can see it right there. And it's very small, and so in order, that's because this is going from 0 to 1 in 1 degree of arc, right? So with only 1 degree, it goes from 0 to 1. So to stretch that out, I'm going to divide by 180 degrees. Now this is confusing for me, and the reason is the y-axis is inverted. So I'm going to invert my y-axis so I get something that more closely matches my mathematical foundation on understanding how this works, okay? So I'm going to change that to negative ry. So usually the angle starts at 0 along the positive x-axis and then increases as you move in the counterclockwise direction and decreases as you move in the clockwise direction. All right, so I'm going to look at the clockwise side of this too. So I'm going to add another equation, copy this, paste it down here, and I'm going to take the negative arc sine right here, and I'll assign that to a cyan color. And so this one is going up. Now you notice it's not very bright, so it really only goes up to 0.5. I could divide by 90, but this will actually work better. So this, it turns out that the arc sine function returns a value between minus 90 degrees and 90 degrees. Okay, so that's what it's always going between minus 90 and 90. Now, if you look at this and divide it into quadrants, we have quadrant 1, quadrant 2, quadrant 3, quadrant 4. So this is valid, arc sine is valid in quadrants 1 and 4, but over in quadrant 2, because it's taking the ratio of v dot y, it doesn't know that v dot x is negative over here. So it just creates a mirror image of what was in quadrant 1. And the same thing down in quadrant 3 just creates a mirror image of what was in quadrant 4. So it's not really valid in those quadrants, although we're just using this to make patterns. So we don't care if it's mathematically valid or not. If we want something that has this sort of symmetry, that's positive on the top, negative on the bottom, has a mirror reflection across it, we could use this. All right. Next, I'm going to look at the cosine value. And I'll just leave these and put in the cosine for each of these. And I have to change this to an x because cosine is adjacent over hypotenuse, which means it's the one that's aligned with the x-axis. Okay, so there's cosine. So this one starts at 0 and increases all the way up to 180. So the arc cosine function is always returning a value between 0 and 180 degrees. And you can see there's no cyan, so it never goes negative. It's always 0 to 180. So that's the arc cosine function. Up in quadrants 1 and 2, the arc cosine function is valid, so it's returning an accurate number. Down in quadrants 3 and 4, it's not. It's just a mirror image of quadrants 1 and 2. That's because we don't use the y component at all in our formula, so we can't tell that it's negative. So it just creates this all positive numbers and a mirror image. Okay, next one I'm going to look at is the tangent. A tangent, and for that one I want to use Vy over V dot x. And tangent over here to the negative side, and it's Vy over V dot x. So it's opposite, which is the y, over adjacent, which is the x. And that looks like that. Okay, so for this one, this is another one that's returning values between minus 90 degrees and 90 degrees. And this one is valid in the first and fourth quadrants, where it's going from minus 90, which would be right. This is negative 90 degrees, up to positive 90 degrees. But then in the second and third quadrants, it's not. It's sort of the, over here in quadrant 2, it's sort of a reflection of quadrant 4. And over in quadrant 1, it's like a reflection of quadrant 3. And that's because when both y and x are negative down in quadrant 3, it can't really distinguish between that and quadrant 1. And the same thing in quadrants 2 and 4. It can't distinguish between a negative x and a positive y, or a positive x and a negative y, because you're taking the ratio of those numbers. So far, none of these has been able to return a full 360-degree angle. So I'm going to introduce arctangent 2. And this one takes two inputs. Instead of dividing v dot y by v dot x, I have both v dot y and v dot x. Same thing down here, the comma. And that one there, now we did it. So this one will go from negative 180 degrees all the way to positive 180 degrees. So it goes through the full cycle, the full range of values for this. And I have it scaled by dividing by 180. So in this range, it's going from minus 1 up to 1. Now we could change this to radians, but if I do, I need to divide by 180 degrees, and radians is pi. So I'm going to use the system variable pi, pi, to divide this by, for radians, like that. And I get the same thing back again when I switch to radians. So depending on if I'm using radians or degrees, I could switch this back and forth. I could make this a custom input, so let's just do that. I'll set these both to A and add a custom input down here. And then I can actually type in the value pi down here, and it will put in 3.142 for a value of pi for this. Now, one other thing I want to mention is the angle input. This will always input a value between 0 and 360. So it doesn't matter what you have your radians set to, this will always put in that value between 0 and 360. So if I set this to 180, and if I divide this by b, then it'll work when I set this to degrees, but not when I set it to radians. All right, I want to cover one last thing. And so I want to compare the oscillator sine function to the sine and cosine functions. So let's look at that. So I'm going to set my equation to empty again and add a new equation. And I'm going to, in this case, create a variable v equals vec2 with x and y, and I'm going to divide by 180 degrees, and then take the oscillator sine of v dot x. So there I have my oscillator. It's going up and down. Now this one never goes below 0, so that's not quite what I want. And so I'm going to use the harmonic version of this by typing an h in there. All right, now it goes down to the negative values. And so, let's see. Now I notice that this one starts at 1 and decreases like a cosine function. So I'm going to copy this and paste it down here into the second equation. And then I'm going to take off the 180, divide by 180. I'm just going to do change this to a cosine of x. And assign that to the green channel. And you can see they match up. Looks like they match up perfectly. Okay, so the oscillator h sine function is identical to the cosine function. Instead of going from 0 to 360 degrees, it has a range of 0 to 2. There is one big difference between these two, and that is if instead of v dot x, I input a vector v. I'm just going to turn this one off for a second and turn on all 3 channels. This will output this texture, and if I look at this corner, it's starting at 1 and then going negative, positive, negative that way, and doing the same thing in this dimension. And then this one starts at a negative 1, then increases to 1 that way. So it's sort of alternating like that to make this checkerboard pattern. Now let's look at what happens when I give this one V. And I'm going to turn this one off and turn this one on. Okay, so that's completely different. So this is actually returning a vector value. So I'm giving it a 2-element vector. It takes the sign of each vector component and returns that. Okay, so this one takes a vector and creates this checkerboard pattern out of it. This one takes each vector component and assigns it to a different channel. All right, let me know if you have any comments or questions, and thanks for watching.